All right, so I've made sort of my own mini version of the periodic table, at least the first 20 elements, and I've drawn all of their Bohr models. Now, if this periodic table looks a little different than the normal periodic table, aside from the fact that there are only 20 elements, you might think that like the left and right side aren't like separated by so much as they usually are. And so I've just used sort of this one column to separate columns 2 from 13. And of course, in reality, there's actually 10 columns between those, but we're not focusing on any of the elements in those 10 columns right now. And so just in the interest of saving space, I've just used one column to separate those. And so what I'm going to do in this video is identify how many valence electrons each of these 20 elements has based on their Bohr models. So starting with hydrogen, well, hydrogen just has one electron, so it's got one valence electron. Okay, so I'm going to write number of valence electrons in green here. Helium's got 2 electrons. They're both in the first energy level, so 2 valence electrons. Lithium's got 3 electrons, but 2 in the first, 1 in the second, so 1 in its outermost level. Beryllium, 2 in its outermost level. Boron, 3. And remember, the reason these Bohr models look the way they do is that the first level can hold 2 electrons, and we fill that first. Then we move on to the second level, which can fill 8. And we need that to be full with 8 before we move on to the third. So on, and then all of the other ones beyond that can hold 8 as well. At least that's how we're going to do it for now. So carbon, 4 valence electrons, nitrogen, 5, oxygen, 6, fluorine, 7, neon, 8. Okay, and then looking at sodium, well, sodium's got 2 in the first, and then 8 in the second, and then 1 in the third. So its outermost level is the third level, and that's got 1 electron in it. So sodium's got 1 valence electron. Magnesium's got 2 in the third level. Aluminum, 3. Silicon, 4. Phosphorus, 5. Sulfur, 6. Chlorine, 7. Argon, 8. And then again with potassium, we are now into the 4th level. It's got 1 electron in the 4th level, so it's got 1 valence electron. And again, it needs that. This last electron needs to go in the 4th level because the 3rd level can also only hold 8. So argon had a full 3rd level with 8 electrons, and then so if we add 1 more to that, it needs to go in the 4th level. And then calcium's got 2 valence electrons in its 4th level. Now, the reason I'm doing this is not just to be tedious, but to hopefully allow us to see a couple of trends here. Well, if we look at it, this first column, these all have 1 valence electron. And then this second column, these all have 2 valence electrons. And then the third column that we're looking at, which is actually the 13th column overall, those have 3 valence electrons, and then 4, and then 5, and then 6, and then 7, and then 8, except for helium. Helium only has 2. So that helium looks to be a bit of an exception. I'll explain that a little bit more in a second. But for now, we can see how the columns, it seems like all the elements in a certain column have the same number of valence electrons for the most part. And it increases each time we go 1 column to the right. Okay. Now with helium, so this rightmost column, column 18, group 18, because the columns are also called groups, for the most part, they have 8 valence electrons, but helium only has 2. However, the reason that helium is placed in this column, what it does have in common with neon and argon is it has a full outer energy level. Argon has a full 3rd level, neon has a full 2nd level, Helium has a full first level. It's just that the first level doesn't need 8 to be full. It only needs 2 to be full. Okay, so that's why helium is placed in that column, even though it doesn't have the same number of valence electrons as neon and argon. Okay. The other trend to notice is if we look at the rows, okay, and the rows are called periods, okay? So this would be row 1, 2, 3, 4. So those numbers are sometimes called periods. And then these numbers for the columns are oftentimes called groups. So with the rows or the periods, each time we go down a row, we are adding another energy level. Or another way of thinking about it is the row number or the period number tells you how many energy levels are in the atoms that are in that row. So the elements in the first row, hydrogen and helium, they only have one, not valence electron, but one energy level of electrons. The elements in the second row, if we look at their Bohr models, they all have 2 energy levels. Or in other words, their valence electrons are in the second energy level. The third row has 3 energy levels. Their valence electrons are in the third level. And the fourth row has 4 energy levels. Their valence electrons are in the fourth level. Okay. Another thing to note with this group numbering. So one way of numbering the groups, again, keep in mind I've skipped over groups 3 to 12 here, which are also known as the transition metals, and those only come in after calcium. Their Bohr models start to get a little bit more complicated. But the other 8, the 2 that come to the left of it, and then the 6 that come to the right, those are sometimes called the main groups. We can number those with this A notation. Okay, so one way of numbering the groups is to just go all the way across left to right, 1 to 18. But the other way is to just focus on the 8 main groups, the 2 on the left and the 6 on the right, the ones that I've shown here, and call them A groups, and then just label it 1 to 8, 1A, 2A, 3A, 4A, etc., as I've done in parentheses up top there. And with those, note how the number in front of the A matches the valence electrons for the elements in that column. Again, except for helium being an exception, but we explained why helium is where it is on the periodic table.